Okay, welcome ladies and gentlemen to section 2.2. We're going to be looking at what's called a power function and looking at something you might remember from last or a couple last years ago called variations, direct variations and inverse variations. Okay, so first of all, let's define what a power function is. A power function can be written as such. If f of x is equal to k times x to the a power, hence the name power function, where k and a are non-zero, which means it's just 1, 2, 3, negative half, negative 7, whatever you want to use there. As long as k and a are not 0, then we can use this as a power function. So here's some things. A is the power, and k is called the constant of variation, or called the constant of proportion. We also call a the degree, like when we are in polynomials, we think about it as degree 2 or degree 3 or stuff like that. We can say that f of x varies as the 8th power of x. So like if a was 2, we could say f of x varies as the 2nd power of x or as the square of x. Just like that. We can also say in a different way, both of these statements mean the same thing. We could say f of x is proportional to the 8th power of x. So we could say varies as or is proportional to, and it means the same statement. If a is a positive whole number, positive value, positive integer, really, then it's called a monomial function like x to the 2nd or x to the 3rd or x to the 4th. So all of those are monomial functions, x to the 2nd, x to the 3rd. Those are all monomial, x to the 4th. So that's really what we're dealing with here today. A lot of this is going to be our monomials without any extra terms, kind of using this lesson as a generalization kind of lesson more than anything extra. So a couple examples here. If I gave you c is equal to 2 pi r, you might know that's the circumference equation. The power of this equation, so the r is my variable, and this is r to the 1st power, and the constant of variation is the number in front. The number in front is 2 pi. We could do something along all of these lines where we have these equations. So a is equal to pi r squared. So we get the area of a circle. This is, by the way, it is a power function. This basically says a varies as the square of r, and the constant of variation would be pi, the power here being 2. This one you got to be a little bit careful here because the power is not 2. This is actually f is equal to k over d squared, which is actually k times d to the negative 2 power. Notice this doesn't have any fractions in it, which means the power of this function is 2, but the constant of variation in this particular case is k. The last one here is v equals k over p, and the same idea holds that since p is in the denominator, that's actually p to the 1st, so it actually becomes k p to the negative 1, so my power is negative 1, and my constant of variation is k. All right, so that's what a power function is. We can call them two different things. We can call them direct or inverse variations. So if it has a positive power, like those first two of those examples, those are called direct variations. Or x varies directly with y. If you have negative powers, like those last two examples, those are called inverse variations. So x varies inversely with y. Or in that last example, p varies inversely. When you look at the word problems in this particular section that asks you to write the variation equation, If they don't use the word inverse or inversely, it's assumed that we're talking about a direct variation. And that's just how we're going to be doing it in this particular textbook. So if they say things like this, the period of time t for the full swing of a pendulum varies as the square root of the pendulum's length L, provided that the swing is small enough, blah, 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 the length of the pendulum. The last little part of that sentence really doesn't have an effect on the equation. But notice that the thing does not say inversely, and it doesn't say directly either. But since it doesn't say inversely, we're going to use directly. So this says t varies. Okay, so t equals. And t varies as the square root of the length. Okay, so the square root of the length. But what's missing is a constant of variation. And I don't care what letter you use. Don't use x, but usually we use a k. So t is equal to k times the square root of L, or in the way I wrote it in the PowerPoint there is telling us that the function is a function of L. So t of L is equal to k times the square root of L. Gives us the direct variation mentioned in this particular problem. All right, quick little reminder here, because you're going to be asked to analyze these power functions a little bit, you need to remember, just so you have this in your notes another time, analysis of a function requires these 7 things. You need domain and range. You need continuity. Is it continuous or not? You need increasing and decreasing. You need symmetry, boundedness, extrema, which is min and max, and asymptotes. Those are ones I enforce. There are 1 or 2 others, but these are the ones that I want us to be doing. All right, get that stuff written down. Make sure that's in there somewhere. Whenever I say analyze this function, or the textbook says analyze the function, this is what you need to put down for analysis of a function. Basically, like if I said, hey, here's x, root x, or that's equal to x to the 1/2 power, we want to say, okay, domain of this is x greater than or equal to 0, or 0 to infinity. Continuity, yes, it's continuous. Increasing and decreasing, it's always increasing. This function is never decreasing, so we would say it's 0 to infinity, the entire domain. This symmetry, none. It's not even odd, so it's none. We can say neither. Boundedness. This particular function is bound to be low at y equals 0. This particular function has an extrema. This has a minimum at the point 0, 0, but it has no asymptotes. All right, so that's a quick little thing. These are easier functions because they're basically monomials. We don't have a whole lot of extra stuff working along with it. So if we were to go to be graphing monomial functions, where you got to remember that n is positive values. It could be negative, but for the most part, we're looking for x actually being positive, not n, or a in this particular case. I'm not sure why I used a there. Should probably be an n. K times x to the a power. Let's look at the possibilities for x is greater than 0. So there are things that we can do here. If we were to just kind of think about what would happen in certain things, in certain functions. Let's go ahead and get a graph going here. If x is greater than 0, so we're looking on the right side of the y-axis, and we need to do when k is less than 0 and k is bigger than 0 in separate cases. If k is bigger than 0, that means we're going to have something like 3x to the a power. Or if k is less than 0, we get like negative 3x to the a power. So let's first look at what happens when a is 1. Okay, so for when a is 1, in this particular case, we get 3x or negative 3x. Let's look at positive first. 3x looks like this. That's supposed to be a straight line. So this is when a is equal to 1. You get a straight line. So that's my x to the first power. And what we need to look at is what happens when a gets bigger. So if a is bigger than 1, you get things like 3x squared, or 3x to the third, or 3x to the fourth. And if you really, really think about it, a quadratic looks like this. A cubic looks like this. A quartic looks like this. You notice what happens over here in quadrant 1. In quadrant 1, all of these functions follow this pattern when a is bigger than 1. They all follow this curve going upwards as we go to the right. And remember, this is for k is bigger than 0, so we're looking at positive. So this right here is for k is bigger than 0. So we haven't reflected across the x-axis yet. Now what happens if a is less than 0? Well, if a is less than 0, my exponent is less than 0, I'm looking at things like 3 over x, or 3 over x squared. Well, all of those functions do this. Now, if you remember from previous classes or whatnot, the 1 over x looks like this. 1 over x squared looks like this. 1 over x to the third looks like this again. And you notice that quadrant 1 all does the same thing here. And my last thing is if a is between 0 and 1. So now we're looking at fractional exponents. So we get like x to the 1/2 power. 1/2 power is a square root. And if you were to compare all of these types of fractions, 1/2, 1/3, 1/4, 1/5, all of them will do this like this. So this one was for a is less than, a is less than 0, and a is between 0 and 1. Well, it's kind of interesting, and it just so happens that this coordinate is 1, comma k. If x is 1, it doesn't matter what the exponent is, it's going to be 1 times the k value. So that coordinate is the same for all 4 of these equations. Now, let's change the pen color here. Where's that? Color. Let's go with blue. Now let's think about what happens when k is less than 0. So k is less than 0 means it's all going to be reflected across the x-axis because that's what it tells me to do. So that means this linear function actually looks like this because it would be like a negative 3x. The a is greater than 1 is going to do this. Oops, that's bad, but we'll go with it. A is less than 1. A is equal to 1. The between 0 and 1 is going to do this. And the a is less than 0 is going to do this. Now, if you look in your book on page 185, you'll see this a little bit better drawing, or actually a lot better drawing than mine, and they use a little bit different colors so they can really emphasize what is happening. But why is this important? This is basically saying I can figure some stuff out. If I was to give you the function 2x to the third power, I can describe in quadrant 1, it's going to do that. And because that's an odd exponent, The function is odd, which means it reflects across the origin down here. So I know automatically that's what 2x cubed is going to look like. If I was to give you 3x to the negative 2, well, 3x to the negative 2, I know because k is positive and it's a negative exponent, it's going to be in here in quadrant 1, but because that's even, it's going to be an even function, and therefore it's going to do this. And I can use this knowledge to just help me know what the parent function is going to look like. And that's really essentially what I need you guys to know is the parent function for any other type of function that we're going to deal with. So for generalizations, let's put it all together here. For k is greater than 0, we're going to start in quadrant 1. For k is less than 0, we do our beginning in quadrant 4. All of these graphs contain the point 1, comma k. If a is less than 0, then x equals 0 is undefined for f of x because you can't divide by 0. That's basically saying things like 3x to the negative 1. Well, I can't have x equals 0 because it'd be 3 over x, and that's illegal. When x is less than 0, f of x can be undefined for my fractional exponents with an even number in the denominator. So things like x to the 3/2 or x to the 1/4 or x to the 1/6. You're trying to find even roots, but it's like x to the 1/2. That's the square root of x, and I can't find that when x is less than 0 because that makes it negative under the radicals. So when I say things like, hey, what does 3x to the 1/2 power look like? Well, it is going to be this. Oops. It's going to be that, but it's not going to be symmetric anywhere because that 2 makes it illegal to have negative x values. However, if I was to give you 3x to the 1/3, this now follows the odd symmetry. So that 3 actually makes it so it's an odd symmetry and does that. But even denominators cannot let you have x is less than 0. These two things here should be reminders. We've done this before. But I'm really, since we're looking at monomials, they're going to be even or odd just depending on the exponent. If the exponent is even or odd, the function is even or odd. So if I was to describe the portions in quadrant 1 and 4 and determine if it's even or odd, oops, come on back here. Jeez Louise. Okay, let's try that again. If I was to describe the portions in quadrant 1 or 4 and determine if it's even or odd, all I have to do is look at, okay, it's x to the negative 3rd power. This is a positive 2. So in quadrant 1, because it's positive 2, it's going to look like this. And because that is a negative 3, it's going to be odd, so it's going to be down here. So I can do any type of descriptions from that. Likewise, if I have negative 0.4x to the 1.5, well, negative 4 means I'm going to start in quadrant 4. This 1.5 is actually 3/2, which means I don't get any negatives here. And because it is bigger than 1, it's going to look like this, essentially. Or that's what it should look like. All right. You guys all got assignment sheets. I am going to leave you with this. And I will see you guys tomorrow. I hope you guys learned a little bit of stuff. Have a good evening.